Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Now what we want to do is we want to talk about something called a titration curve. Now, specifically acid-base. You recall when you do a titration that you're adding usually a base to an acid, and then you're waiting for it to reach the equivalence point where the moles of the acid equal the moles of the base. So a classic example would be like HCl plus NaOH makes water plus NaCl. But if I'm adding this until I reach the equivalence point, you could be plotting the pH with a pH meter. And so you'd find at the beginning, if I have the acid in the bottom beaker, if you will, right? So we've got a beaker right here, and we've got the acid down here, and then we're adding the base to it. The pH would start low. I put my pH meter, little device, a meter, pH meter. It would start out low. And then it would keep going up and up and up, but just a skosh. And then the interesting thing, it would jump right away. All right, right here. And that would actually, and what you'd find is, in this particular instance, you would find the middle of this inflection point to be right at 7, and this right here would be said to be the end point. So in a titration curve, it goes like this, and boom, and the middle of the inflection point is the end point. And the pH, you would say, well, it's always 7. Okay, it's 7 if this is a strong acid and this is a strong base. But it changes if you've got a strong acid and, say, a weak base, or a strong base and a weak acid, or all these different combinations. So let's actually talk about the other combinations. So let's take the case of a weak acid like HF and react it with NaOH. Now HF is the acid. We'll put that at the bottom, and then we'll continue to add the NaOH down here. That's going to make water and F negative. And if you recall from the last video, the salt of a weak base, the salt of a weak acid is a base. And so since the HF is a weak acid, it's not going to have a low pH, it's going to have a bit of medium pH. And you're going to start higher, and as you go up, it's going to look more like this. And the interesting thing is, the pH at the equivalence point, the center of the inflection point, will be higher than 7. And the reason for that is that the F negative, right, is the salt of a weak base, is an acid, or the salt of a weak acid is a base. This is a base. You're making a base. The pH of the equivalence point is going to be higher than 7. And then you could do another one. We could take a strong acid, HCl, and react that with NH3. All right, we can still leave our acid down here and our base down here, but it's going to change the graph. All right, because when we start this, it's going to start with the HCl down here, but it's going to be more like this, and the pH is going to be less than 7, because what you make is you make this compound ammonium, all right, plus the chloride, and the ammonium is an acid which will keep the pH lower. So this graph right here is a strong acid and a weak base. And then the last one would be a weak base with a weak acid. So I can take hydrofluoric acid plus ammonia, and what you would get there is you would start in the middle. You'd have just kind of like this. Sometimes this is almost impossible to find the inflection point. And actually, will the pH be 7, less than 7, more than 7? It depends on the relative strength of the HF, all right, versus the ammonium, because this would make ammonium. Which one is the stronger acid versus the stronger base? I don't know the answer. And this could shift, but notice the size of the inflection point is different. And one last titration curve that's kind of confusing for a lot of students. If I have, for example, H3PO4, phosphoric acid, which has 3 hydrogens, we call this a triprotic acid, and we react that with, say, sodium hydroxide. That's a weak acid with a strong base. An interesting thing that's going to happen is you're going to see it go like this, and you'll end up with 3 inflection points, because you have to get rid of the first hydrogen, hydrogen number 1, then the second hydrogen, and then the third hydrogen. So you end up with actually 3 inflection points. Now, as a note, it's usually easy to see the first one, hard to see the second one, and the third one is sometimes almost impossible to see. So what I found when I've done these experiments is you find the first inflection point, and if you're trying to find the third inflection point, which is the real equivalence point up here, is you times it by 3. So if this was at 10 milliliters, this will have to be at 30 milliliters. So when we have an acid that has more than 1 hydrogen, This is called a triprotic acid because there's 3 hydrogens. This is a monoprotic acid, and like H2SO4 is a diprotic acid. Then we can have different inflection points. For a diprotic acid, I think you probably can figure this out, the curve would be like that. Notice that the first one is more pronounced, the second one's less, if you're doing that, say, with sodium hydroxide. So titration curves, kind of complex, but they're awesome because they tell us so much about how acids and bases work.